Hi everyone, I'm Shouvik Choudhury, a distinguished postdoctoral fellow at the Academy Sinica Institute of Astronomy and Astrophysics in Taipei, Taiwan, and I'll talk about neutron mass and mass ordering, constraints from cosmology, neutrino oscillations, and beta decay combined. So this talk is based on the following paper of the same title, and this was written around 2 years ago, and the lead author was Stefano Gariazzo. So to introduce neutron mass and mass ordering, I first start with neutron masses, which are the only direct evidence for beyond standard model physics. And active neutrinos have three mass eigenstates, which are quantum superpositions of the three flavor eigenstates, which are the electron, neutrino, muon, neutrino, and tau neutrino. And some of neutron mass eigenstates is this quantity that you can see on screen, and tightest bounds on some of neutron masses come from cosmology, because cosmology is sensitive to the neutrino energy density, which is proportional to some of neutron masses at late times. And the most popular bounds in literature at 2 sigma or 95% confidence level in lambda CDM plus sum of neutron masses model is 0.12 EV circa 2018, and then 0.09 EV when we got the bound updated with Boss data release 16, and then 0.072 EV with CMB combined with Daisy Brown, which is the latest results. But considering the prior from normal ordering, this bound is 0.113 EV. So the inverted ordering is not ruled out with very strong confidence even in the lambda CDM model with the latest cosmological data. Now, the favor eigenstates can be written in terms of the neutron mass eigenstates, where U is the PM&S matrix, and the favor transition probability in vacuum is proportional to this sine square of delta m square, where delta m square is the mass square splittings. Delta, we know from oscillation experiments, we know this delta m21 square and modulus of delta m31 square. So we know that at least 2 out of the 3 mass eigenstates correspond to neutrinos which are massive, but one of them can still be 0. And since the sign of delta m31 square is not known, there are 2 possible orderings. One is the normal ordering, where m1 is less than m2, less than m3, and there is also the inverted ordering, where m3 is less than m1, less than m2. For normal ordering, the minimum required mass is 0.06 eV, whereas for inverted ordering, this is around 0.1 eV. Now, to give the depiction of the mass ordering, in case of normal ordering, m1 and m2 are at the bottom, and m3 is slightly higher up, whereas for the inverted ordering, m1 and m2 are at the top, and m3 is the lowest mass eigenstate. Now, if we use this notation that capital L is for the largest mass, M for medium mass, and S is for smallest mass, then we can define normal ordering as L square minus M square minus M square minus S square greater than 0. And for inverted ordering, this would be less than 0. So we'll use that for any 3 given masses. We can use this condition to define, to say if it is normal ordering or inverted ordering. Now, I would also like to introduce beta decay, which also constrains neutrino masses. So beta decay of tritium gives you a helium atom along with the electron and electron antineutrino, and energy released of this decay is 18.6 keV, and this is carried mostly by the electron and the electron antineutrino together. And the highest energy electrons can put a bound on the lowest neutrino energies, and hence the neutrino mass. In the Catherine experiment, it is actually sensitive to the effective antineutrino mass square or mu square. So, and the latest bound on this is 0.1 plus minus 0.3 EV square, which corresponds to mu less than 0.8 EV at 90% confidence limit. And but with the current sensitivities, experimental sensitivities, it is safe to approximate mu as sum of neutron masses divided by 3. So from Catherine, we approximately get this sum of neutron masses less than 2.4 EV at 90% confidence limit. And so this bound is much weaker than cosmological bounds. Now, I'll introduce Bayesian analysis and model comparison in the context of data sets. Now, so we usually use the Bayes theorem, where A and B are different events. So we can use data for A and theta, the parameterization for a particular model M as B, and then we can write the Bayes theorem as posterior multiplied by evidence equal to likelihood multiplied by prior. And the posterior is basically the posterior distribution that we get given the likelihood, which is usually supplied by the experimental collaborations, and the prior belief of the distribution of parameters that the analyst assumes. And this posterior distribution is, of course, an important quantity in cosmological parameter estimation or any kind of parameter estimation where Bayesian analysis is involved. And given the probability normalization condition, we can get the evidence by integrating out the right-hand side of the equation number 2. And so for parameter estimation, of course, we are interested in the posterior distribution of the parameters, but when we are interested in Bayesian model comparison, then evidence is the most important quantity. So if we apply Bayes' theorem again, only on the model and the data, then we get this equation. And if we have two models, M1 and M2, then given a particular data set, their probabilities probability ratio will depend on the evidence ratio as well. Now, typically models, before any data is introduced, models are assigned the same prior preference, then PM1 is equal to PM2. And in this case, given a particular data set, the probability of the two models will depend on this evidence ratio or Bayes factor. Now, in case of neutrino oscillations, normal ordering and inverted ordering, there are only two possible models, and then PNO plus PIO will be equal to 1. And then you can define the odds N versus IO as the Bayes factor. And we typically quote log of B. And the thing is that to get a 5 sigma evidence for normal hierarchy over inverted hierarchy, we need this log B to be more than 14. And so Bayes factor has to be 10 to the power 6. But for less than strong evidence, we need Bayes factor close to 150. Whereas for strong evidence, we need Bayes factors more than 150. Now, but for conclusive evidence, we need this 5 sigma confidence, this 5 sigma value of log B, which is 14.37. Now, priors are also quite tricky because in cosmology, we are interested in usually a flat prior on sum of neutral masses because that is the quantity constrained by cosmology. But let's say you wanted to put flat priors on individual neutrino masses, and let's say there are only two masses, M1 and M2, then flat prior on the individual neutron masses would not lead to a flat prior on sum of neutron masses. It would actually be a triangular shaped prior. So the lowest masses and the highest masses will get suppressed in the posterior, and the probabilities of the priors in the middle would be enhanced. And this is not something you want. And the thing is that if we are varying M1 and M2 separately, then to get flat prior on sum of neutron masses, we will need priors of this shape to actually get this flat prior on sum of neutron masses. So it is important to remember that while varying individual neutron masses, it's not usually it's not always that the priors you assume on M1 and M2 and M3, let's say, will lead to a flat prior on sum of neutron masses. Now, another thing is relative entropy or Kullback-Leibler divergence here between two probability distributions of a continuous random variable, which is given by this equation. And if you assume P to be the posterior and Q to be the prior, then you can write it as this. And the thing is that DKLM, this for a particular model, this basically measures the information gain from prior to posterior. So if prior and posterior are the same, then this is log 1, and this integral will tend to be 0, whereas if you have information gain from prior to posterior, then DKL will be higher. So this basically means that if we have a higher DKL, that means the prior is less informative. And that is what we want in a Bayesian analysis, that our prior beliefs are not affecting our posterior distributions that we get from the data or observations. Now, in neutrino mass ordering, we consider 5 different parameterizations, which are cases A, B, C, D, and E. For case A, we consider a parameterization which was considered in a previous paper, which claimed to have a strong evidence for a decisive evidence for mass ordering, which was the normal ordering. And so for case A, here we consider a Gaussian prior on the logarithm of the 3 masses. The Gaussian prior is described by this mean log mu and standard deviation sigma, which work as hyperparameters. And then all the masses are drawn from this distribution. And after this, we order them and assign values to the mass eigenstates M1, M2, and M3 as per the considered mass ordering. So we have total 5 parameters, 3 mass parameters, and 2 hyperparameters, mu and sigma. And while sampling, we consider a uniform prior on the logarithm of mu with bounds like this for mu and sigma. So this seems like a complicated prior, and it is. And so this is what gives strong evidence for neutrino or mass ordering, the normal ordering in a previous paper. Then we study case B and C, where we apply uniform prior on the masses in the range. For case B, we apply this extra uniform prior over case A. And we apply uniform prior on the logarithm of the masses using the same mass range for case C. So for case D, we consider a separate scenario where we are considering 3 parameters where M lightest, delta M21 square and delta modulus of delta M31 square, and we consider the same range for all 3 parameters and impose a uniform prior on the logarithm of these parameters. So this is case D with log priors. And then later we also consider uniform priors on these parameters instead of their logarithms. And there's a reason for that I will come to later. So in case E, we consider the standard scenario where we use uniform priors on sum of neutrino masses, delta M21 square, and modulus of delta M31 square with this prior range of 10 to the minus 6 to 10 for all three parameters. So we are using very broad parameters, very broad prior range for all the parameters concerned. Now, so in data sets, we have first the neutrino oscillations, and we impose the following Gaussian priors on delta M21 square and mod of delta M31 square. So our main goal is to show that different prior choices, A, B, C, D, E, can do drastically different results. So we do not perform a full-fledged analysis using full oscillations data or cosmological data or beta decay data set. So what we do is use this simplified analysis, and in this case, for neutrino oscillation, we impose these priors. But using these priors, it is expected that we get a Bayesian base factor of 1 because we are not imposing any preference for N or IO by using these priors. So later we include delta chi-square oscillation of 6.5 in favor of normal ordering. This is obtained from global analysis of neutrino oscillations data by another paper, and this contributes to a base factor of 26 to this BONOIO, which corresponds to a reference of around 2.1 sigma. For Catherine, we use this mu square equal to 0.1 plus minus 0.3 V square, this bound that we use a simplified likelihood where we use this simple log likelihood where we use 0.1 as the mean value and 0.3 as the error bar of sigma. Now, we are taking an approximation of mu equal to sum of neutron masses divided by 3, or basically it is equal to 1 neutron mass value. So from data perspective, since sum of neutron mass is less than 2.4 eV is the constraint from capturing data, it is unlikely to change the base factor by much. Now, from cosmology, we use the two results of 0.12 eV and 0.09 eV bounds at 95% confidence limit. So we again use very simplified Gaussian likelihoods where the mean value is 0 and the standard deviations are half these values, which is 0.06 and 0.045 in the two cases. So these are Cosmo 1 and Cosmo 2 likelihoods. So previous analysis with uniform prior on MLI test, which was this analysis done by me, had shown that N versus IO odds ratio of 3:2, which is inconclusive at best in various cosmological models. So this was with the 0.12 EV 0.12 EV result. But in any case, even with 0.09 EV, we are not going to get a very high confidence, very high evidence for normal ordering. So cosmological data also would not contribute very much to the base factor. Now, and we come to the results, and what we see is that for case B and case A, case B, and case C, we get, when we use the Cosmo 2 result along with Catherine and oscillations experiments, we get very large B values, or the value of base factor, which correspond to strong evidence for normal ordering, whereas for case D and case E, we see that the base factors are much lower, even with the strongest data sets, which and this evidence corresponds to a preference for normal ordering of around 2.7 sigma. So what is happening? So one thing is that if we consider the KL divergence values for normal and inverted ordering, what we find is case B, E, and case B and case D, and in the uniform prior case or the linear prior case, and case E, these show high KL divergences, whereas case A, case C, and case D with linear priors show lower KL divergences, which means that the priors themselves are deciding the results and not the data sets themselves. So this is one issue with this case A, case B, and case D with log priors. However, one thing here to note is that there is a large difference in the base factors depending on the strategy followed to sample the neutrino mass parameter space. So case A has 33 times the base factor of than case D, and this shows that the results strongly depend on the chosen parameterization and priors. And so base factor for case D remains unchanged when we move from log prior to uniform prior. However, the KL divergence changes. So for case D, log and linear prior give the same base factor. However, since KL divergence in the case of the log prior is much lower, we would suggest that people use uniform priors. And KL divergence in cases of A and C are small, implying that the priors drive the results instead of the data. And and we find that the KL divergences are high in B, D, and E, where case D has uniform prior. And so in this case, this implies basically that the results are least dependent in these scenarios on the prior choices. So for case D, we get a base factor, as I said, which is 145, which corresponds to a non-conclusive or 2.7 sigma preference for normal ordering. And out of this, 2.1 sigma comes from oscillations data and only 0.6 sigma from cosmology. So in extended cosmological models, the mass bound can relax by a factor of 2, which would correspond to even smaller contribution to the base vector. And so one needs to understand that in the current the current constraints from the AC bow are quite strong, but the preferred cosmological model for the AC bow data combined with CMB and supernovae data is actually the dynamical dark energy model. And given that the bound on some of neutral masses is around 0.2 eV from the data sets, so in that case, cosmological data sets contribute to quite a small value in the base factor. So it is not likely to change our results given in this talk, as long as your preferred cosmological model is the dynamical dark energy model. And even with the lambda CDM case, we expect only a moderate increase in the evidence ratios. So it will still not reach the 5 sigma level. And apart from providing a high KL divergence, one needs to understand the prior should also be ordering agnostic. That they should not prefer a particular mass ordering even before the data is introduced. So as you can see that in the case B, we have high KL divergence. So one might ask that why not take the base factor provided by the case B parameterization. And there we are, there is the issue of ordering agnostic prior. So here, what we see in case A, that if the 3 neutrino masses are randomly drawn from a large number of, times from a log normal distribution, then sorted into this L, M, and S, large, medium, and small, then we see that for particular sigma values, this parameterization already prefers the normal ordering over inverted ordering, and this is not really desired quality in a prior choice, because in that case you are already preferring the normal ordering over inverted ordering. So in case A, if we use the normal distribution, then it would be ordering agnostic, but the previous paper had used the log normal distribution, and that is why we studied this case as well. So in case A, we get a very large preference for normal ordering even before introducing the data, so it is not really ordering agnostic. And same is true for case B as well. If so, even though KL divergence is high, case B also prefers a normal ordering over inverted ordering at 1.6, whereas case C prefers it at 2.7, where the 3 masses are drawn from the uniform prior on the log of the masses. So that's case A, B, and C are not ordering agnostic, but case D and E directly sample the mass splittings from the same distribution and thus are ordering agnostic by default. So case D, uniform prior, and case E seem to be good prior choices that maximize information gain from data while maintaining ordering agnostic behavior. Thank you, and please ask questions.